occur between the outer bands That's assuming that the structure is symmetric. For non-symmetric problems, that's an interesting thing to think about, which I'll leave it up to you. So more precisely, fill-in occurs to the right of non-zeros in L. So if we look at the non-zeros in L, fill-in will occur to the right. So for instance, well, there's nothing over here, but fill-in occurs to the right. And in U, fill-in occurs to the bottom of the non-zeros in U. So below the non-zeros in U. To the right of non-zeros in L and below non-zeros in U. So suppose that we have a sparse matrix, not this one, okay? Do we always have fill-in in every position between the outer bands? If we have some sparse matrix, and we're going to do Gaussian elimination without pivoting on it, fill-in will be created. Do we always get fill-in in every location within the bands? What do you think? So who thinks yes? Who thinks no? Okay, so the no's win by a very small margin of most people not voting because they don't care who is the next president. But it is correct. So the answer is no. Okay, so we'll generally get fill-in within the bands, but there could be zeros within the bands. So that's something that is interesting to know. So here's an example, just a 4x4 example. Okay, so we want to eliminate this element. So let's say if fill-in occurred within always, then we would get a fill-in over here and a fill-in over here, right? But if we eliminate this element over here, this adds onto that non-zero. If we eliminate that element over here, this adds onto that non-zero. You can see that no fill-in is created. Okay, so we may not fill in everything within the bands. Okay, so an important concept that I want to talk about right now is that reordering the rows and columns in the matrix can reduce the amount of fill-in. Okay, so we had a certain amount of fill-in here, but in fact we don't have to live with that. We can reorder the rows and columns to reduce the amount of fill-in. And here's an example, but before the example, let me write the title. Reordering the matrix rows and columns can change the amount of fill-in. Here's just a matrix that is 4x4. Okay, so apply the Gaussian elimination process to this symbolically. Okay, and you'll see that we get fill-in in all of these extra positions. Okay, so these will all fill in. These should be red X's. If you're using color, just use red X's. So fills in entirely. And now consider the original set of the original matrix, and we're just going to order the rows and columns in reverse order. Okay, so that gives us a matrix with this structure. And now apply the symbolic Gaussian elimination process, and you'll see that there's no fill-in at all. Okay? And if you have a problem, AX equals to, well, AU equals F to solve, you could reorder the equations, okay, but you can still recover the original solution. And just to illustrate that quickly, suppose you have AU equals F. Okay. To reorder the equations, we might specify it like this. So PAP transpose, where P is something called a permutation matrix. Okay. So here I've used the same permutation for the rows and columns, but we don't have to use the same permutation for the rows and columns. Okay. And I'm going to write U prime there equals PF. So I'm going to permute the entries in F as well. Okay. And this gives us, so a property of permutation matrices, by the way, is that the inverse of a permutation matrix is equal to its transpose. Okay. So U prime is equal to, not U prime, U is equal to P times U prime. Okay. So once we solve the equation using the permuted matrix and the permuted right-hand side, we can recover the solution of our original equations by, again, another permutation. So this is just to say that we can permute the matrix as we like, and we don't worry about later on down the line. We still are going to recover the original solution. In fact, I think I'm missing a transpose, right? Okay, so now we know that these reorderings are safe things to do. Okay, what are good orderings to reduce the amount of fill-in for Gaussian elimination? Okay, so here we use the natural ordering of the variables, and this was the fill-in. So the question that we have now is, what orderings could be good for Gaussian elimination? I'm going to abbreviate that by GE for reducing fill-in. So one idea that you might have immediately using this heuristic that fill-in occurs between the outer bands is to try to find an ordering that reduces the bandwidth. Okay, so that is just one simple idea, and we'll talk about that. And there are orderings for that. And orderings for that are called level set or breadth first orderings. Okay, and then we'll talk about a couple others as well. One is called nested dissection. ND. And the other one is called minimum degree. MD. Okay. But before we talk about these orderings, I need to say something about the graph, as in graph theory, the graph interpretation of a sparse matrix. Okay. So every symmetric sparse matrix and there are graph interpretations for non-symmetric matrices as well, but we'll keep things simple. We'll talk about the symmetric case. Every symmetric sparse matrix is associated with a graph. Okay, so a graph I'm going to denote by capital G. And a graph is a set of vertices and a set of edges. Okay, so these are vertices, and sometimes I will call them nodes, depending on my mood, but it should not affect things. Okay, and this E is a set of edges. Okay, so for symmetric sparse matrix, let's say with n equations, the set V is just the set of indices 1 to n. Okay, and the set E, okay, is the ordered pairs ij, the set of ordered pairs ij, such that aij belongs to, no, I don't mean to write that, such that aij is non-zero, and I'm going to say I is not equal to j. Okay. So for each non-zero in the sparse matrix, I'm going to get this edge. There will be a corresponding edge joining the vertices. And I'm going to ignore the non-zeros that are on the diagonal. This is the A, this is the I not equal to J. Okay? For PDE discretizations, like the one that we just saw, then the graph is related to the mesh. The graph G over here is related to the mesh. So we can say, well, so given this sparse matrix, not the pink elements, okay, just this sparse matrix that we drew originally, what is the graph? Okay, the graph is very simple. It is just this thing, where we have the nodes at these intersections. And it's labeled 1, 2, 3, 4 up to 16. So these are the vertices labeled 1 to 16. There's a non-zero between 0 and 1, a non-zero between between 1 and 2, and a non-zero between 1 and 5, but no non-zero between 1 and 3. Okay, so this is the graph corresponding to this, and of course it comes from the PDE mesh. And how about for this example? There's also a graph. Okay. So if we label the vertices, okay, so we have a 1, and then we have, it's connected to 2, 3, and 4. Okay. And I think there was another example, which I probably have erased. But I think the concept is simple. I won't do further examples. And I show this graph because we need this concept of neighbors. So for each node, this node has a number of neighbors. This node 6, or vertex 6, has neighbors 2, 5, 7, and whatever that one is. Okay? So nodes have neighbors, and you can think of essentially variables having neighbors if you want to extend the analogy to differential equations. Okay, so now that we have this concept of graphs, we can talk about our first ordering, which is these level set or breadth first orderings. Level set. Breadth first orderings. And as I said before, these are orderings that try to reduce bandwidth or something related called profile. So these reduce matrix bandwidth. Or profile. And bandwidth is defined as it's just one number. Okay. So for any matrix, it's just one number. And it's the maximum of I minus j for all aij that are non-zero. Okay, so for this matrix, you might want to see what the bandwidth is. Okay. And something called profile. Profile is essentially all, so the bandwidth is really has to do with, only depends on one element, right? So if you have one really bad element that is far from the diagonal, then the bandwidth is going to be really bad. Okay? To be more precise, we might measure something called profile, which is we'll look at each row and we see, well, how far is the farthest non-zero from the diagonal? And we add this up over all of the rows, and that will be the profile. So we're going to add over all the rows the distance from the diagonal, I minus fj, where fj is the minimum value of j. Sorry, this should be fi. So these should be fi's. So fi is the minimum value of j such that aij is not equal to 0. Okay, and this assumes that the diagonal is non-zero. And the idea behind level set or breadth first orderings to try to reduce the bandwidth or the profile is to try to reorder the matrix such that two equations are numbered nearby if their corresponding nodes are nearby in the mesh. Okay, that was a long sentence. Let me write it down so you can parse it. Let me read it again if my handwriting is too messy and maybe for the camera. Want to reorder the matrix such that two equations are numbered close to each other if their nodes are nearby on the mesh. Because the nodes that are far away on the mesh will give us large values of Fi and ultimately large values of the bandwidth. Okay? So let's see how we might want to do that. Let me just start with this simple example. So we have a number of nodes, each one over here. And let's say we're going to start with one of the equations. We'll just pick one of them. I'll just pick this first one. Okay, so this is the equation that I'm going to number first. Which equation should I number next? How about this one? Not really a good choice because it's far away. I don't want to number it nearby. Okay, so a good choice might be this one over here. Okay, so suppose that's 2. And how about the third equation? Which node should I choose for the third equation? How about this one? It's good for 2, but not necessarily good for 1. Okay. So now we have a hard choice. We might choose this as 3. Okay. Just because 1 was already here, we don't want to leave 1 far away from everyone else. Okay, and we might proceed in this fashion to choose 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? And what we've done by doing this, you can see that approximately nodes that are nearby are numbered nearby. Okay? And what we have done is traversed this graph using a breadth-first ordering. Okay? And there are a number of algorithms that you can use to take a graph and to find such a breadth-first ordering. I think possibly we have some time to write that down. So I'll try to write that down quickly. So breadth-first search or breadth-first ordering. Let me just write breadth-first ordering. Okay, so what is the algorithm? We're going to start off with some vertex I that is in the corner of the mesh. Okay? And sometimes this is called a pseudo-peripheral. A pseudo-peripheral vertex or pseudo-peripheral node. Okay? And let's mark I as seen. In other words, we want to visit all of these vertices, and we want to keep track of which ones we've seen already and which ones we haven't seen. So we're going to start with 1, and we're going to mark it as seen. And now what we're going to do is we're going to put I on a queue called Q. And a queue is a data structure in which you put things in, but you take things out in the order in which you put things in. So the first in, first out concept. Okay, so we're going to put I on a queue. And then we're going to loop while Q is not empty. First time through, it's not empty because we just put something in it. So we're going to remove the first element, remove whatever is at the head of the queue. And let's call remove first element from Q And then let's call it I. So this I is the first element that we removed. That's not this I, which is the pseudo-peripheral node. And put I on the list P. So we're going to keep a list as well. And the elements in the list are going to be in order is going to be the ordering of the elements. So we put I, the first element, in here. So that's going to be the first element in our ordering. Okay. So we remove this element, and now we're going to look at the neighbors of this element in the graph. This element of I in the graph. So loop over neighbors of I. And the neighbors of I I'm going to call J. Okay, so here vertex 1 has two neighbors, 2 and 3. Okay. And unfortunately, I've run out of board space. I'm going to try to continue down over here. So I'm going to loop over the neighbors of I. So if J has not been seen, then we're going to put J in the queue. Okay. And then end if, end loop, and end while. Okay, so this is an algorithm that comes up with the ordering. So the elements are going to put inside this list P into ordering that we are going to visit them. And if you apply it to this matrix with this graph with the corner as being the first vertex, then you'll see something like this. Okay. Something I want to point out is that if we loop over the neighbors of I, which are called J, in a particular order, in order of increasing degree of vertices of J, then we have something called the Cuthill-McKee ordering. Okay. So I'm going to maybe write that over here. So in Cuthill-McKee ordering, abbreviated CM, we're going to talk about reverse Cuthill-McKee ordering later. Put J in the queue by increasing degree of J. By increasing degree of J. I don't have room to write this. I'm going to write it on the side. Okay, so that's called Cuthill-McKee. And we'll see why Cuthill and McKee decided that this might be a good thing to do. So why is this called level set ordering sometimes? If you look at, if you group the nodes into partitions such that each partition contains nodes that are the same distance from the root or pseudo-peripheral node, then that defines a level. Okay? So a level is a set of nodes that are the same graph distance from the root. There is a very well-known ordering, which many of you may have heard of, called RCM, and it stands for reverse Cuthill-McKee ordering. Okay? Reverse Cuthill-McKee ordering is basically a breadth-first ordering with the special thing that Cuthill and McKee decided, which is to order by increasing degree, where degree is the number of neighbors of a node. Okay? Order by increasing degree. So that's Cuthill-McKee ordering. Reverse Cuthill-McKee ordering is to take that ordering and to reverse it. Seems like a weird thing to do. But it was observed that if you do that, you can reduce the amount of fill-in better than Cuthill-McKee. I think this is very embarrassing for Cuthill-McKee because they introduced this ordering. They said, oh, they wrote a number of papers. This is our great ordering. And then someone, just a few years later on, they said, well, if you just reverse the ordering, you get something that's better. OK, so that's called reverse Cuthill-McKee. And we'll maybe have time later on to say why it might be better. It's a very interesting question. So reversing the Cuthill-McKee, the CM ordering, has been observed to usually give less fill-in. Okay, so some interesting questions that you might think about to help you understand reverse Cuthill-McKee is that when you reverse the ordering, the profile changes. Okay, the profile doesn't stay the same. Okay. Another question you might ask yourself, well, suppose that you have Cuthill-McKee ordering. It has a certain bandwidth now. Does the bandwidth stay the same when you reverse the ordering? Those are some questions you might think about a little bit on your own to try to understand what the effect of reversing the ordering is. Okay. So why do we want to order by increasing degree? And to try to understand the answer to that question, and also to talk about this other ordering called minimum degree, I need to talk about the graph interpretation of fill-in. Okay, so remember that trying to reduce the profile is not exactly the same as trying to reduce the amount of fill-in, because some of the entries within the envelope or the profile might be 0 anyways, right? As we saw one simple example already. So this is why I said that these orderings try to reduce the matrix bandwidth, which there are many applications of it, and we'll see others later in the course. But there are methods that try to explicitly reduce fill-in. And minimum degree is one of these. And to try to explain that, let's try to first talk about the graph interpretation of fill-in. And I'm going to do the same example. Okay. And we're going to assume we have some ordering. This is the natural ordering, etc. And we're going to apply Gaussian elimination. We have to have an ordering to have a matrix defined so that we can do Gaussian elimination. So we're going to apply Gaussian elimination basically to this matrix here in this ordering. And in Gaussian elimination, we eliminate columns one at a time. This corresponds to eliminating vertices one at a time. Okay, so in the first step of Gaussian elimination, we're going to eliminate this first vertex. Okay, so we're just going to erase that vertex. And what happens is we're going to join all of the vertices that were connected to the first vertex. Okay? And if there was not originally an edge between 2 and 5, then we've created a fill-in. If we go back to this original picture, you'll see that between 2 and 5, there's a fill-in. Okay? Now we're going to eliminate 2. So we're going to erase 2. And we're going to look at what all of the neighbors of 2 are, 3, 6, and 5, and we're going to join them. Okay? 6 and 5 were already joined. So we're going to need to join 3 and 5 and 3 and 6. In other words, we form a clique. Clique is a term in graph theory. We form a clique between all of the vertices that were joined to the vertex that we've eliminated. And if these were not original edges in the graph, then these are fill-in edges that have been created. So we'll come back over here and we can see that 3 and 6 there's a fill-in, and 3 and 5 there's a fill-in. And we can continue this process all the way. Okay? And in general, if we look at some pair of vertices, 8, 9, 10, 11, 12, 13, 14, 15, 16, we could ask the question, well, is there a fill-in at 10, 12? Right? It's not an edge in the original graph, but if we do the factorization, is there fill-in there? One way you can tell whether or not there is fill-in is you can look at the original graph and see if there is a path in the graph between 10 and 12 that involve vertices that you have already eliminated, meaning vertices that are numbered less than 10 and 12. Okay, so is there one? So where's 10 and 12? So 8, 9, 10. So this is 10. And 12 is over here, right? So I think that there's going to be fill-in. And in fact, there is a path. And it is this one. So when we eliminated 6, 7, and 8, this would have created enough of these new edges to create an edge between 10 and 12 by the time we eliminate 12. Okay, so it's a way of looking at the original graph and seeing, well, is there going to be fill-in? So it's a very useful trick to be able to tell how much fill-in you might need and what those locations might be, although there are more practical ways than what I've just described. Okay, but this is called the graph interpretation of fill-in. Okay? So the minimum degree algorithm, which I'm not going to write down, I'll write down next time, but I want to also give you an exercise, so I'm trying to save 5 minutes for that. So the minimum degree algorithm is to start with some vertex, 1, okay, and eliminate 1. So here we don't have any, let me redraw this. So we don't have any numbers anymore because we want to find an ordering. But we have to start somewhere, so let's start over here. Okay. So we're going to eliminate this, and this is going to join two things together. And now which is the one that we should eliminate next? So you can see that fill-in is created by joining all of the vertices that are neighbors. So if the vertex has a small number of neighbors, then fewer fill-in will be created. So you want to choose the next vertex to eliminate that has the fewest number of neighbors. Okay? So this has degree 3, this has degree 3, this has degree 4, so you don't want to choose that. But there's actually a better one. You could choose this one, which only has degree 2. So maybe this one is the next best one to eliminate. And you can see it's a very different ordering from the ordering of breadth first search. Okay? And it gives you an ordering that is not banded. But generally, it gives you an ordering that has less fill-in than if you try to order for bandedness. Okay, so that's the minimum degree ordering. I'll write it down next time. But what I'd like you to try for tomorrow is a simple exercise in MATLAB to try to see what the effect of some of these orderings are. Okay? So here's your first exercise. How exciting. So try and compare different orderings in MATLAB. Okay? And I'm going to write down a set of MATLAB functions that you can try on your own. First, we need to generate a matrix. And let's generate a matrix in the natural ordering. And there are a number of MATLAB commands you can use to do that. We're going to first generate a grid. Okay? So numGrid. And if you don't know these functions, you can type help numGrid, and you can see a lot of documentation on each one of these functions. So we're going to generate a square like we did in our example. And let's say that we want to do an 8x8 problem, an 8x8 mesh. You could use different values of meshes. You could use different domains shapes as well. Okay, so this will give us a grid. And to give us a matrix corresponding to the Laplace operator, or just the diffusion part of that operator that we talked about. So A is equal to del squared, the del squared operator of G. Okay. So now A is a matrix of size 64 by 64. Okay. And you can look at what this matrix looks like by using the SPI function. Right? And you could also type A and return, and it will show you that the matrix is sparse. It's not storing the zeros in the matrix. Right? So SPI A is going to give you a picture that looks like this. And MATLAB has a number of orderings that are available, including RCM. It has RCM, but it doesn't have Cuthill-McKee. So nobody really uses Cuthill-McKee, but RCM is available. And to come up with that ordering, you could say P is the symmetric RCM of A. So you give it a matrix A. And P is a vector here. This is not a permutation matrix. This is a vector. Okay, so you can construct a new matrix. Let's call it A2 is equal to A P comma P. So this reindexes the matrix A using this ordering. So now you have A in an ordering which is RCM. And now you could do SPI again, okay, to look at what that structure looks like. And you could also do L is equal to the lower triangular, well, the upper, maybe, I guess MATLAB does the upper triangular, so let's call it R. R is the upper triangular Kluski factor of A. And maybe R2 is the upper triangular Kolesky factor of A2. And you can see what is the number of non-zeros in R and what is the number of non-zeros in R2, and see what is the number of whether or not reordering has reduced the number of non-zeros. And that's the number of fill-in in the matrices. Okay. So besides RCM, another ordering that you can use is called AMD, which stands for approximate minimum degree. Minimum degree is a fairly expensive ordering algorithm, so there are approximate algorithms that are almost as good but are much faster. So these are two to try, and next time we'll talk about minimum degree more formally, and also nested dissection, which I didn't have time to show you. But otherwise, we're out of time. Thank you very much for your attention, and if you do have questions, please just send me an email. Question, yes?
The function SYM, CRM or RCM?
This is RCM, sorry. Thank you. Any other questions that might benefit everyone? All right, see you tomorrow.